Thank you. So, thanks for the introduction. And also, I would like to start by thanking the organizers for inviting me in this nice conference. So, this is a quite right time to talk about the prospect, or the first of all take a stock of the current situation in the SUSY as a new physics, and also talk about the prospect in the light of future upgrades like HL-LHC and things. Now, today I'm going to talk about the status of SUSY spectrum generators in the light of HL-LHC, High Luminosity LHC. So I'll start very briefly, because in this audience, I don't have to give a lot of introduction. So what we know at the end of round 2, that the Higgs mass is measured to be very close to 125 GeV with the errors being 0.2-ish. Then from the morning talk by Manoranjan, we came to know that the supersymmetric particles at the end of round 2 are ruled out. For example, gluinos are up to 2.2 TeV. Stops are of around 1.3 TeV, and so on and so forth. So now, also, if I had looked at some of the projections for HL-LHC, and I could see that some of these simulations are telling me that the supersymmetric particles at HL-LHC will be probed. Can be probed around 2 to 3 TeV for gluino, and 1.5 TeV to 2 TeV for stops. Now, so even we are in the SUSY spectrum, other than Higgs, there are a lot of other particles like the supersymmetric partner of tops, supersymmetric partner of bottoms, and other things. But so far, since we have not seen any hint of this SUSY partner, so what we have at hand at the moment is the Higgs mass, its properties. Now, what I wanted to say is that this Higgs mass itself will tell us a lot about where the SUSY spectrum lies. Okay. So for that, I'll just go through very briefly about the Higgs spectrum. So first we need to understand the Higgs spectrum. So in the supersymmetry, there are two Higgs doublets, up type Higgs and down type Higgs, and their hypercharges are +1 and -1, and the supersymmetric potential is given by this, where there are D terms, there are F terms, and there are mass terms also, and there are also these B mu terms. Now, so the wave at the end in the symmetry breaking happens at a scale where the first order derivative with respect to this doublets, neutral part of the doublets are 0, and then from there we get the Higgsino parameter and the B mu parameter, whereas the tan beta is the ratio of the waves. Now, if you look at the 3-level spectrum, it's basically consists of one pseudoscalar Higgs, and then another charged Higgs, and it's a pair of charged Higgs, and the CP even light Higgs, which is MH, and the heavy Higgs, capital H. And if you see that, if you just look at the MH square, the light Higgs mass, at the 3-level itself, this is below Z boson mass. So the thing is, that means that that is kind of quite quite expected, the way the SUSY is broken in the minimal setup. Now, if we see that, so then that means a large one loop correction, large radiative corrections are there to pull the mass above the Z boson mass. And in this case, I'm going to talk about the stop and the stop loops, enhanced corrections of the lightest CP even Higgs boson. And this, in the case of no mixing between the two stops, the mass square corrections goes like this, where you can see there is a log of the MS, which is a SUSY scale, M SUSY by MT. Now, if we turn on mixing between the two scale, okay, so before that I should say that, so to pull the mass, so from here you can see that if we push the SUSY scale higher, or make either or both the stop mass is heavy, we can get large corrections. But there is another way to do that, which is basically the mixing, introducing the mixing. And as you see that apart from the log factor, there is also term which is proportional to the mixing parameter between the stops, which also adds the same order to the one loop corrected Higgs mass. And if we demanding that either of the stop masses are below 1 TeV, and this one loop corrections adds around 20 TeV of the tree on top of the tree level mass, and thus evades the LEP limit. Now, the point is, as we have seen at this point, that there are two ways to make Higgs mass heavy. One is to make the stops heavier, or we can introduce large mixing between the two stops. Now the point is, at least at the end of run 2, what we are seeing, the stops are pushed above 1 TeV. So for the rest of my talk, I probably won't be I'm talking much about this large mixing scenario, but rather than it's on the large mass scenario. Now, what I was saying that, so we saw in the beginning that the Higgs mass is measured, the error is around 0.2 GeV with 125 GeV the central value. So now what happens in all the spectrum generators, what's available in the market is that, so those starts with a good assumption, which was like where the SUSY scale is not very far from the Z boson mass scales. And then the standard model couplings, gauge couplings, or the Yukawa couplings, they are converted from the MS bar values to the DR bar values. And then they are directly used as a input to the SUSY spectrum, in the input to the SUSY spectrum calculation. And most importantly, the Higgs masses, which we are calculated this way, are done at the fixed order. So that means at a fixed order of alpha S or YT or YB in the full supersymmetric model. In this scenario, where the supersymmetry scale lying is expected to or assumed to be lying close to MZ. But as I was telling, that with the LHC exclusion limit pushing the SUSY particles above 1 TeV or so, these approximations actually is not a very good one. So in this case, these kind of fixed order Higgs mass calculation are less and less accurate due to the presence of large logs. So which we have seen in the previous case. See, this is log of m stop 1, m stop 2 by mt square in the large logarithm presence in the calculation. So now these are not these will come as an theoretical uncertainty. There are other parts of theoretical uncertainties. For example, from the MS bar to on-shell scheme, changing of the scheme, changing of the renormalization scale, and so on, so things. But if we sum up all of those theoretical uncertainty, it adds up to around 4 to 5 GeV for this fixed order calculation, which is well above, as I was telling, that the current uncertainty of 0.2 GeV. Okay, you can take a 3 sigma value of this 0.2 also. So what is important with the present measured value of Higgs is that to precisely calculate the Higgs mass in such a scenario, which will, and in this precise calculation of Higgs mass will also affect the visible or the viable spectra of particle masses. In this case, for example, the largest contribution comes from the stops. Now, so because of this, because of SUSY scale being pushed higher above and above, so in the recent days, there have been a little bit of change or shift in the way Higgs masses are calculated in the supersymmetric generators, particle generators. So let me first talk a little bit about this, the old one, or which you call the fixed order one. So in the fixed order calculation, the masses, so there is a scale called Q match, where the QED QCD or the standard model is matched with the MSSM, and above the Q match, above this scale, there is a full MSSM RGs which are there, and we calculate the Higgs mass at this Q match. Now, in the case of fixed order calculation, the MH, the Higgs mass is calculated using some known higher order diagrammatic corrections. For example, we know up to 3 loops and partly of the 4 loop calculations, which are of the order of alpha 3, alpha T, alpha 3, alpha V in this order. Now, with pushing the MSUSY higher and higher, the higher order corrections becomes more and more important because there are large logs, those has to be resummed, and also there are some parts of existing 3-loop terms, for example, alpha t square, alpha t square, alpha 3, this term is not has not yet been calculated, and those terms are missing. There are some missing terms in the 3-loop also. So these becomes important as we push the SUSY scale to higher and higher values. So now this kind of put forward a new approach which we call the effective field theory approach. In the effective field theory approach, so it's basically, we can call it like a 2-scale matching instead of the fixed order, which is a 1-scale matching. In this EFT scheme, what happens that below MSUSY, the only standard model degrees of freedom exist, and we match the standard model to the MSSM at MSUSY. Now, from MSUSY to MA-MZ, or the electric scale, only the standard model RGs are run, and that most of the spectrum generators have now moved to 3-loop standard model RGs. Now, MH, which is earlier calculated at Q match, now it is calculated at MZ, but using the effective standard model quartic Higgs coupling lambda SM from this matching at MSUSY. Okay, but there is a little bit of caveat in this case also. In this way of doing EFT scheme, one actually neglects terms of order mz by MSUSY square. So this EFT scheme, as we know that EFTs are good approximation when there's a large scale separations. So as soon as the scales are close by, these EFT schemes are doing not very well. So I don't go into much detail because I think Pietro is going to, there's a dedicated talk by Pietro Slavic on this process. So I'll just flash about what are the spectrum generators, currently available spectrum generators with fixed order calculations, like this suspect, which is been used for a long time. There, the SUSY Plab, the homegrown spectrum generators, Spheno, the version 3, soft SUSY, the older version of soft SUSY, some older version of fine Higgs. So they have the fixed order calculation with different precision level, but these are fixed order. But then the new, so most of this, a part of these spectrum generators have also evolved or also adopted the new EFT scheme. For example, Spheno 4, soft SUSY 4, fine Higgs, some newer version, as well as the new member in this group is a flexible SUSY, which also is a C++ code which does this job. This does calculate the Higgs mass in the EFT scheme. So now I'll try to go directly to the comparison of light Higgs mass. So for example, on the left panel, what we see is that in the comparison of light Higgs mass, so the left panel is calculating is plotted the light Higgs mass as a function of the scale, as a function of the mixing by the MSUSY scale for different MSUSY masses, and this is done with flexible SUSY 2.0. So there, as you can see, that with increasing the SUSY scale, the Higgs mass is also increased. This is basically due to the due to the large logs appearing in the loops. Now on the right panel, as you see, is that here what is compared is that the soft SUSY with the with this okay, in this case there are two things. So first of all, this black dotted one is the EFT approach, and the blue dashed and the red solid is the fixed order calculation. So now you can see that that as the SUSY scale is lower and lower, the EFT approach, the error is super large, is getting larger. But as soon as we are above, say, 2 TeV SUSY scale, the EFT approach, EFT scheme, Higgs calculation, the error is diminished, whereas exactly opposite happens for the fixed order calculation, either for soft SUSY or the of the flexible SUSY case, which is shown in the red dashed ones. Okay. Now, so here, so now if we go further and then compare, we can compare between two two popular codes, for example, fine Higgs and flexible SUSY, and there what is compared for example for large mixing and large tan beta. So the fixed order calculation is compared with their errors with the EFT one, and there's something called hybrid one. So first of all, what is the hybrid one? So hybrid one is, as I was telling, that the EFT approach neglects order of log mz square by m SUSY square terms. So as soon as m SUSY is close to mz, the EFT approach has larger errors, which you can see here by the gray area, gray region. But what hybrid method does is actually tries to calculate some fixed order calculation whenever m SUSY is close to mz, and moves back to the EFT approach as soon as m SUSY is above, say, 2 TeV or so. So in that way, the red one, as you can see, is probably is at the moment the best way of the best precision we can get from the theoretical calculation of the light Higgs mass. So now, as I was telling, so these two codes are very similar in the numerical values, and this hybrid approach is available. The hybrid approach can be applied to both the codes. Now, what happens? So about what happens to the spectrum if once we move from the fixed order calculation or the old scheme to this new one, which is the 2-scale matching scales. So now, as I was telling, that the SUSY masses are defined at ms, right? But the main changes in this EFT approach comes between the ms and mz, being the SMRG running instead of ms SMRG. So to see an effect of SUSY spectrum at ms, so if we have just this running of ms to mz, the RG runnings are not that much. So to see the effect of this new scheme, one needs to go to this the unified, so where the SUSY boundary conditions are given at a much higher scale, for example, M Sugra or for example, GMSB or all those cases. So in that case, you can see the change. So the different contours or different regions are on each panel are actually says that the difference between the old and the new scheme for the case of stop masses. So as you can see that it's not more than 3% for the case of stop. Tau, it is even less than like 1%, less than 0.05%. Okay. Whereas for the case of charginos and gluinos, they are the similar. So the largest contribution basically comes from the stop cases. It's mainly because there's a large contribution coming from the G3, the QCD coupling running. Now, if we further go detail into the case where there are large stop mixing. So this one was with stop mixing 0, but this one with stop mixing, the maximum being the maximum one. So in that case, we can see that even in the same parameter space, we could get larger contributions. And for example, in the right panel, so the left panel is for stop mixing positive, or the right panel is stop mixing negative. So in that case, the change in the masses between the old and the new schemes are more prominent. Okay. So now, so how am I doing on the time?
You have still 10 minutes from the start of the clock.
Okay.
But,
so then I can.
We are 20 minutes late already. So I'll appreciate if you, yes.
Okay, I'll take 5 minutes. Okay, let me.
Yes.
So maybe I'll just wanted to show a couple of things. So here, so I'll just flash one thing. So what is this EFT scheme? So the EFT scheme is like this. So we know the standard model Higgs mass. say defined at a scale m SUSY, should be equal to the full theory of MSSM. So these two masses should be equal. These are the pole masses. Now MHBSM, or like MS in this case of MSSM, is basically the running mass m small h BSM square, and minus this is the sigma h is the threshold correction, and th is the tag poles. So just from this equation itself, one can calculate the lambda, the effective quartic coupling in this in the theory, in this full theory, and match the full MSSM theory to standard model effective theory at MSSM at m SUSY. And using this lambda, one runs down to the electroic scale and then calculates the Higgs mass. So this is like very sketch in a cartoon way of telling how these EFT schemes are done. Okay, maybe I'll also just flash a little bit of things. Like there you can see that different, so the Yukawa couplings and mostly the top and bottom Yukawa, there is also perceptible change in the between the old and the new scheme. Same goes for the G1, G2, and G3, G3 being the largest one because of the color factors. So now probably this brings to me the summary. So what at the present is that we see that the non-observation of SUSY particles at LHC run 2 has pushed the SUSY scale above 1 TeV. That's what we've seen. The run 2 results are telling us. Then such large SUSY scale has profound impact on the Higgs mass calculation done by the SUSY spectrum at the moment, the fixed order calculators. So due to this high SUSY scale, the EFT approach has become more and more indispensable tool to calculate the Higgs mass by these spectrum generators, and the errors are much better under control in the EFT approach, even if we push the SUSY scale, say for example 10 TeV to 100 TeV also. Okay, I'll finish with that. Thank you.